So we are going to this is the last segment we have for the lectures on features. And last time we were talking about SIFT features, so we'll finish that segment today. And I think that's the last segment for this lecture. So we were talking about, so we went through what is like the overall approach we have for extracting SIFT features, and what were all the different characteristics of this kind of feature. So in SIFT, what we do is we try to first identify the key point locations, or you can say like interesting point locations. And to do that, we look into like blob kind of structure. Okay, and to detect these blobs, we have this Laplacian of Gaussian kernel. And again, it's a very basic filtering operation. So during filtering, you just use this kernel and see if this kind of pattern is present in your input image or not. And you say that, okay, that's like the interesting point which you are actually looking for. And you do that at multiple scales. And again, the idea is like if the scale of your image is actually varying, then this will make your algorithm scale invariant. Now, this is I will say is the core of SIFT algorithm. And this slide actually tells you exactly how the SIFT features are extracted. Okay, so I think we briefly went over this again. Let me do a quick recap of this. This is your input image, and these are like all the kernels at different scales. And you, as you know, like we discussed last time, this kernel is actually Laplacian of Gaussian, which you can also say like double derivative of Gaussian. And what you do is to define these kernels. So when you're taking the derivative, the Gaussian function you will use, that will have actually different kind of standard deviations. Okay, so you're kind of increasing the standard deviation for a Gaussian function to obtain these kernels. And then again, you perform filtering using these Gaussian kernels on the input image. And it's going to detect like, you can say like these are, you can say interesting points, but mostly we are looking edges here. And again, we are detecting that at different scales. Okay, so that's like the initial step. Now the crux is how exactly we determine whether like a pixel location is a key point or not. Okay, so what you do, so whatever step I'm going to explain, you will repeat that step for all the pixels on all these heat maps, which are coming from different scales. Okay, so we'll just discuss one pixel location, but you will repeat that for all the locations. Okay, so let's say we are interested in this scale, which is the 4th scale. So we will take this heat map, and again, this is just showing like you the grid formation, or you can select grid format for the same heat map. Now, let's say we are looking at this pixel location. What we'll do is we will try to look the activations of the neighboring pixel locations. Okay, so all the green ones. And while we do so, what we do is we look the neighbors which are in the current scale. So exactly this heat map. In addition to that, we also look into like the other scales. Let's say the scale which is greater than this one, and the scale which is less than this one. All right, so these two. So these are the pixels, the neighboring pixels, okay, the green ones, and this is coming from 5th scale. So again, what we do, so these are like all the neighbors of this pixel. And similarly, you'll have neighbors for all the pixels in all these 4 or 5 heat maps, right? So for each pixel, you will see if it's a maximum or not, okay, or it's minimum or not. If it's maximum or minimum, you will say that that's your key point, and that's what you are interested in. And you will just record like the XY location of that pixel. And you will also record like from which scale it was coming. For example, for this pixel, if it is like, let's say maximum or minimum, we'll have XY location for this pixel, and we'll have scale as 4. That's the 3rd parameter. And this is like all we need. So similarly, we'll collect like, we will collect all the key points in these different key maps. And then that will be a long list whenever we find like a maximum or minimum. And then you say that, okay, these are your set of key points. So that's how we determine key points in SIFT algorithm. And this was something interesting. Instead of computing double derivative for your filter, what you can do is you can actually approximate that using difference of Gaussian. So we discussed this briefly last time. If you have two Gaussian kernels with different standard deviation, you can actually just subtract those two Gaussians. And that difference is going to give you a function which looks exactly like inverted Mexican hat, which is your Laplacian of Gaussian function. Okay, so you don't have to compute derivatives, which is kind of expensive because you have multiplication operation there. Instead, you just compute difference of Gaussian, which is computationally cheaper than multiplication. All right, so let's see how we can use this difference of Gaussian. Okay, so what you do is you first like blur your image with the Gaussian kernel with a standard deviation of sigma. Okay, so this is like the the pre-processing step. Then you again blur your image with a different Gaussian kernel, which is k times sigma. So k is your scales, like how you are varying the standard deviation of your Gaussian kernels. Okay, and then you simply subtract 2 from 1. Okay, so this is your image, and this is you have smoothened this image using Gaussian kernel, the first Gaussian kernel, and this is like the second Gaussian kernel, which has a slightly bigger standard deviation. That's why it's blurry. You subtract these two, you got this image, and this is exactly like what you will get if you smoothen your image using a Laplacian of Gaussian kernel. Okay, so that's like a very, very interesting approximation. Now, how you can use that when you are computing features for SIFT? You can simply use like multiple scales of Gaussians, right? For example, in this case, you have just sigma and k sigma, but you can have multiple scales. You just keep multiplying with k, which is like the multiplicative factor, and you can compute like smoothened images like these. Okay, so that will be your smoothened image, and then you can just keep subtracting them. Okay, so this is subtracted from this, and again this is subtracted from this. So you keep doing that over multiple scales, and these are your response function, or you can say like response activations after difference of Gaussian, and this will be like a approximation of your Laplacian of Gaussian as well. Okay, so this is like the same step which we discussed right over here. Okay, and then we perform this operation on those heat maps to get the list of key points. But here you will see like you have a different stack as well, and this is called octave. So in this octave, you have multiple scales. Now what you do, you like stack multiple octaves on top of each other, and the difference is, in this case, you were changing the size of the kernel, right, the Gaussian kernel, but you do that for different resolution of your images. So in this case, you are reducing the resolution of your image, and you keep doing that. You can have multiple octaves. So now you can see that you are actually making this algorithm scale invariant from 2 point of view, right? So the first is you are actually using your kernel, which has a different standard deviation. So that's taking care of multiple scales. And you're also performing filtering on like differently sized images. Okay, so at 2 level, you're actually taking that into account. And again, you will repeat like the same process for this stack as well. And again, from this, you will try to find out the key points. Okay, so yeah, this is just like trying to visualize the steps I showed you earlier. And you smooth your image, and you get like, again, you smooth from a different standard deviation, you subtract. So you can keep doing that, okay, as you increase your standard deviation. Right. And at the end, you will take these and you will figure out what are the key points. Again, this is the same step. It's nothing new. Okay, so for each pixel location, you're just trying to figure out whether this is maxima or minima. If it is, that will be list of key points. So once you do that, then the result you will get will look something like this. So all the yellow circles over here were actually detected as key points using the filtering operation, which we discussed in the previous slide. Now you might like see one interesting aspect here, right? So these key points have like the scale factor as well, because the radius of the circle which you are plotting, it's actually varying a lot. You have smaller circles, you have bigger circles, right? So that size of the circle is actually representing the scale. So at what scale you are actually detecting this key point. All right. And what may happen is, like, at one location, you might have multiple scales as well. So that key point could be like being detected as key point for varying scales as well. So that's why you can see like it's actually cluttered at this location so you have like all these key points here, right? And you can see you have smaller ones, then you have bigger ones. Okay, so this will be like a long list, of course, because this was done at like multiple scales and multiple kernels. As I said, like 2 different aspects there. Now, once you have these key points, then the next step was, so this was like the second step, right, in your SIFT algorithm. The next step was you will extract some kind of features from those locations. Now let's try to understand how we can do this. And this is going to be somewhat similar to when we're discussing about HOG feature extractor, right? So what you do, let's say this is your key point. Then you will know the scale of that key point. Okay. So what you do, let's zoom into this. You will see something like this, right? Then what's going to happen is, for each pixel location, when you perform filtering, right, then you can compute gradient orientation. Okay, you find gradient in X direction, gradient in Y direction, then you can compute the orientation the same way you did for HOG features. And that way, for each pixel location, you will have some kind of orientation. And what you do is you use that orientation to compute this kind of histogram. Okay, so for each patch, you can do something like this. And then what will happen, you actually keep those orientations which are clearing some kind of threshold. And you will just ignore all the other orientations. Okay, for example, this particular patch, you will have all these pixels, right? And for every pixel, you will have some kind of orientation. So this is just showing histogram of that. And then you can see that multiple pixels are there which have this orientation. This is like, let's say 20 to 29 pin, right? So a lot of pixels have this orientation. Again, a lot of pixels have this orientation over here, which is, I think, around 300. So then these two are the most prominent orientations you have for this particular patch. So you will keep these and you will just ignore all the other orientations. And then the idea is you will say that, okay, at this pixel location or at this key point, you have 2 different orientations. One is this 20 degrees and the other is like 300 degrees. Okay, so one key point can have multiple orientations. So that's how you compute orientation for your key points. Now, once you have the orientation, then the next step is you try to normalize that. Okay, because what will happen if your images are rotated, then we have seen earlier, right? It's very hard to actually compare those two, right? Because the pixel locations will be shifted and the orientations will be different. So to take that into account, what you do is whatever orientation your algorithm has detected for a key point, you use that to normalize all the key point locations. Okay, so the idea there is, let's say you have this key point location and the most dominant orientation, let's say, was in this direction. Okay, so this is showing the histogram for this on the right here. Okay, so this one is the most dominant one. Right, so the bin will look like this. So what you do, you normalize this, mean you make this dominant orientation like pointing towards north. And that's again just one way. You can normalize in any other way, but whatever you do, you should do that consistently for all the key point locations. So in this case, I will show you how you can normalize everything towards the north. So in this case, what will happen, if you shift towards north, then you know this angle, right? Let's say this is 45 degrees from the y-axis. So you will shift all the orientations towards 45 degrees towards left. Okay, that's how you normalize. You can see like all the orientations you have at this patch location, you're just rotating them with this angle. So the idea is whatever the most dominant orientation you have, that will always point towards north. And again, this histogram is just shifting because your orientations will change. But of course, like this is going to be your most dominant one. And after your adjustment or after your normalization, always like this first pin will have the maximum value because that's what you're trying to do. Okay, so that's how you normalize your orientation. And once you have normalized, then it's the same HOG like a based algorithm where you try to compute local features in this window around the detection. Okay, so what you do is you have the 16 cross 16 window, which is like 16 pixels by 16 pixels. And then you try to rotate, so you will normalize. And the other factor, you also have scale, right? Different key points will have different scale. So you will take that into account and you will only crop like this 16 cross 16 window based on that scale. For example, if the scale is very big, your patch size will be big, but again, you will have to do some adjustments. You can select resizing to make it 16 cross 16. So one example could be like if the scale is very small, it could be in that region you don't have 16 cross 16 pixels. Then you'll have to perform some kind of interpolation, or you can say extrapolation, right? To make it 16 cross 16. And then you can just compute gradients, okay, for that window. And again, you can use a smoothing filter or not. So all that is fine. Okay, so this is like the step which is shown here. So each of these bounding boxes is actually showing you key point. And the size of that bounding box is the scale. So if the bounding box is smaller, the scale was smaller. For example, this is like pretty small here, right? And the orientation you have, that is actually the orientation which is dominant in that at that location, at the pixel location. Now what you will do is you will adjust or normalize the orientation. So you will rotate that patch, right? And then you will also resize that patch to 16 cross 16. Let's say if it could be anything else, maybe 30 cross 32 as well. But 16 cross 16 is, let's say, just one example. And again, that's one parameter which we'll have to decide. And you extract that patch. And you can see here that all these patches are 16 cross 16. And for all of those, like the orientation has been fixed. So they are like completely perpendicular. Right. So now what you do next is for each block, which is 16 cross 16, again, you already have computed those edges, right? You have performed smoothing, so you don't have to do that again. So just reuse those values. And again, for each pixel location, you will have these orientations. Now what you do is you will extract like the HOG kind of features, which we discussed in the previous segment. Okay. And again, this is shown, I think 8 cross 8, but again, that's a parameter. So if it's 16 cross 16 window, you will have 16 cross 16 cells here. Okay. So you similarly break that bigger block into smaller cells, let's say 4 cross 4. And for each cell, which is 4 cross 4, you will have to extract a histogram based on the orientations and depending upon how many bins you have. So in this case, if you have 8 bins, so again, you will divide your 0 to 180 degrees to 8 different bins, or 0 to 360 degree into 8 different bins, and create that histogram. And you will do that for each cell. And in total, you have a 4 cross 4, 16 cells. Your feature will be 128 dimension long. Okay. So if you divide that into 4 cross 4, each cell is 4 cross 4, you will have 4 different cells. And for each cell, you will have a 8-dimensional histogram. And again, you just concat those like you were doing for HOG feature. That is going to give you 128-dimensional feature vector. So then at the end, what's going to happen is, let's say you have a given image, you detected all these key points, which will be a long list. Then for each key point, you will extract a 128-dimensional feature vector. And depending upon how many key points you have, that will decide like what is the size of your feature vector for that particular image. Okay, so again, this is just a recap of that. This is your 16 cross 16 window, and you are dividing like your window into 4x4 cells, and each cell is 4x4. So what you do is you take each cell, let's say this one, you compute orientation for each pixel location, and then based on all the orientations you have in this cell, you can actually create a histogram. For example, if there are 8 bins, you can have 8 different values for that, and then you will have 8 values for each cell. Then you can just concatenate for all the cells you have in this block, and that's going to give you your SIFT feature descriptor. So again, once you have the descriptor, you can perform all those like post-processing things, for example, normalization and all. So this is again same as HOG. It's nothing new. And again, normalization, you can have different variations, right? So we discussed that you can have L2 norm, you can have L1 norm, or you can do like double normalization. First normalize, maybe clamp higher values, and then again renormalize, right? So all those are different variations, but the whole idea is you just want to normalize your feature vectors. So that was SIFT descriptor, and again, a little complicated than HOG, but if you think about this, it's kind of combining both your corner detection, which has ideas from filtering and edge detection and all, and then combining that with HOG, how you can extract features from your edges. So it is like in a way a complete package, and it gives you very good set of features, and it's still used like today because the features are actually very powerful. And one thing I would like to share is, we are currently actually doing some research on these local features, for example, SIFT. And still today, like after all these years with deep learning research, there are some aspects or some areas where SIFT features are actually much more powerful than the CNN features. Okay, I won't share more about that, but of course, if you're interested, you can come to office hours. I will be happy to talk about it. But it's like ongoing research and like something interesting I wanted to share. Okay, so this is like a quick recap of local descriptors, and so most of these features which we have studied, they are based on histograms, right? HOG was based on histogram. Then even SIFT, we were computing histogram of gradients. And you can have templates as well. So template is something when you are filtering, when you're performing filtering, right? So that in a way, for example, even the Laplacian of Gaussian, that's the template you're actually looking for in an input image, and you can change that template. Okay, so and then it's combination of these two most of the times. And again, these are just like very common properties which we want to have in these features. They should be robust, they should be distinctive, and of course, they should be compact and as well as efficient. Okay, and so far we have seen like most of these descriptors are actually just focusing on edges or gradient information, which is interesting. But of course, like we can have some descriptors which are maybe only utilizing color information as well, right? For example, if we have some problem where color plays a very important role.